Myself, Mohammad Wadwani, and today I am going to present our work, Cog-VADU, a training-free cognitive reasoning framework for video anomaly detection and understanding. This work has been recently accepted in TMLR, Transaction on Machine Learning Research. So before driving into our methodology, we will see the introduction to video surveillance. So video surveillance is about security and monitoring activities around the residential and commercial properties. More generally, video surveillance is about video anomaly detection, where we have to distinguish between normal and abnormal activities. So let's go through the examples. So as you can see, so let's see the two examples. One is the normal example and another is the abnormal video example. This is the normal video where the normal activity is going on, and this is the abnormal activity. Not the abnormal. This is the abnormal activity. So, so this is the current literature survey where that we have done. That These are the current literature surveys currently is basically divided into two main methods. One is this non-explainable methods, and another is explainable methods. Non-explainable methods are those where these are basically the traditional vision only methods where they are utilizing the video and visual features to extract the anomaly information. But in case of explainable methods, they are utilizing both visual information as well as some textual information. So, and the output is also in terms of this textual information as well as this output is also in the form of textual information. So the limitation in case of this non-explainable methods is that they lack the semantic information. In that case, we don't know what actually is. We just have the information about the anomaly scores, but we don't know what actually is happening, who is doing the abnormal activity, where it is being and where the abnormal activity is being done. So we don't know about those. And also the main limitation of those explainable methods is that non-explainable methods is that they lack the generalization. Like in one data set, we need to we get a separate parameter set, or we can say checkpoints. In another data set we have a different checkpoints, so they lack the generalization. So coming to this explainable methods, they have better generalization as they are being trained, as they are built on the foundation models like vision language models, which has been trained on large data sets. So they have better exploration for this anomaly detection. And also the advantage is that they have semantic information. They also provide the output in the form of textual information. That's also one of the advantage. But the disadvantage of current vision language based video anomaly detection methods is that they need training data sets. They need the curation of the training data sets. They first they just require they just utilize some traditional anomaly detection component for which they need training, and after that they also need to fine tune this multimodal LLM, where they basically use this LoRa adaptation. For that, they also need some instruction tune data set. So thus, they need heavy annotation data sets. Also, the another disadvantage of those methods is that they just use the simple prompts whether there is any anomaly or not. They did not utilize the prompting more well. So for that, what we have proposed, our method is this Cog-VADU, where we utilize a training-free method. This is a training-free pre-trained model. This is a pre-trained model, vision language model, where we have utilized an advanced chain of thought prompting to get the things done, like to know what actually is happening in the video, whether this is anomalous or not, what is the anomalous score, why it is anomalous. We are able to get those. So, so in short, this is the summary. This is our methodology. Like we have introduced this Cog-VADU, cognition, video anomaly detection and understanding. That's a novel training-free video anomaly detection method. by utilizing pre-trained large vision language models. We have proposed this chain of anomaly detection thought prompting that enables a stepwise and temporary coherent reasoning. We have developed this cross-modal re-ranking stage that aligns text reasoning with visual representations. And we also find some problems in the current annotation datasets. We have tried to improve the annotations as well. And we have achieved a we have achieved as competitive zero shot results alongside with the highly interpretable outputs. So let's go with our architecture. So this is the architecture of our methodology Cog-VADU. As you can see, first this is a pre-trained model that's freeze. We divide the video into the segments and then we pass the model those segments. For example, first we pass this segment zero, and we pass the video segment and we pass this our chain of anomaly detection thought prompt, and then we get some response. Then that response for the segment zero is added with the prompt, and it is passed with the segment one, and similarly we get a response two. That segment response two is added with the segment three, and in this case we get a response four. In this way, we are able to get some temporal information by utilizing just this feedback. So this is basically a RAS stage up to this point. After that, we have this refinement stage. Uh, the RAS scores are further refined by this refinement stage where we utilize this cross-modal refinement strategy. And at the end, we are doing this soft mix weighted score aggregation, and then we are getting a clean refined scores. Now let's go. Now we know that by building this, in order to build this model, we need some components like we need those we need this the design, we need to select, we need the choice of this multi-model, we need the prompting, and then we need those refinement strategies. So for that, first thing is this choice of the multi-model. We have tried to evaluate on further on some available vision language models. Then we find that here this video llama 3 is providing a better results and better detection metrics as compared to other models. So we choose video llama 3 as our base model. After that, the another thing is prompting. As we know that prompting plays an important role. It is a driving force for any LLM or vision language model. So the current methods, they are just utilizing a simple prompts like describe this scene. We also try to evaluate those prompts, and we find that as this prompt is not containing any kind of prior information about the task, so it is not able to, and it is not able to generate the response that is of our interest. So as you can say, that is creating some just a general explanation of the scene, but actually the person is trying to steal some things from the text. So when we try to improve our prompt, like we went to prompt two and we try to put some more things into the prompt, we try to put some prior information, we try to define the task. Then it in this case, our in this case the model was able to catch the anomaly very betterly as compared to previous. We so after that, on the basis of those two, we just propose this chain of anomaly detection thought prompt, where we do this perception first, like we get the description about the, we first make the model to analyze the visual information to know what is the interaction between the people, objects, actions, environment. And then we, after that, we also try to provide this temporal context in the form of this feedback. After that, we are trying to put the model in some cognitive mode to analyze this to provide some reasoning what actions are going there, what actions are going, whether these are normal or abnormal, why it is abnormal. And then we are also asking the model to utilize this prior information in the form of this anomaly database. And then on the basis of the severity present in the video, we are asking it to generate the reasoning, some stepwise reasoning, then anomaly scores, and then anomaly type and some severity levels. So this is the evaluation of the prompting techniques. At this we can see this is the simple prompt. As we can see that it is not performing very well. Then as we go on improving the prompt, the performance is getting more better and better. So after that, this is The evaluation. So this is the evaluation of our prompting. That is the CO, chain of anomaly detection thought prompting. This is actually the ablation study of the various components that are present in our prompt. As you can see, as we added some more components after this, just when we added this temporal feedback, it helps us to uh, stabilize the RAS scores like this temporal feedback. After that, this full Cog-VADU is the result of this RAS stage plus refinement stage. This is the actual result of the refinement stage. So after that, this is more information about the refined stage. That initial anomaly score predictions are made without full long range understanding, and then because they we just pass a clip and some just one clip previous context to the LLM and to the large vision language model, and it generates the rationale. So it lacks the global information. So for that, we utilize this cross-modal refinement strategy where the video segments are rescored using retrieved multimodal contextual signals. And for this, we utilize this image and video and textual encoder. And then we retrieved context with the RAS scores. And then at the end, we did the softmax segregation. So this is the evaluation of the refinement techniques. We also did some ablation here, like we take direct textual and the visual, and then we did the retrieval. In that case, the performance was not that good. Then we try to do that retrieval based on visual only, like we tried one segment versus all segments. This was also not this gives some better performance but not very much. In that case, the anomalies were getting diluted. After that, we added our own this cross-modal ranking system where we got some better performance as compared to previous. This is the ablation of various parameters that is being present that are present in our refinement strategy. The first is this actually the weights that are we providing with the with this textual and the during the retrieval of this during this weighted sum of this textual and the visual information where we do this re-ranking. So at that case we find that this by taking m is equal to 30 samples at a time and then considering alpha textual and alpha visual as zero point 0.5, we get a better performance. So during our evaluation, we also find that the data sets that there are basically two major data sets for video anomaly detection. This is X-ray valence data set and UCF-Crime data set. We find that the data set is not the data set misses some anomaly regions as well as it misses this cause and effect regions. As you can see, the original annotation is up to only this point. It has been labeled as anomaly, but they are missing this anomaly, so we are trying to cover this anomaly as well. As you can see, this is our anomaly. And in the second case, this cause and effect has been cause and effect in some frames up to some frames has been taken as anomaly, but rest they have missed it. So we have tried to cover up those anomalies as well. This is a statistics and of our re-annotated data set. Like this is the 22.5% in the number of anomaly frames that has been added to the UCF to the XT valence dataset, and similarly 39.1% for UCF-Crime dataset. And this is the number of repetition bias and the inconsistency cause effective frames that has been added to the newly re-annotated dataset. So these are the quantitative results on XT valence and UCF-Crime dataset. As you can see, we have tried to annotate both on the original, we have tried to evaluate both on the original annotation as well as the re-annotated dataset. We can see that our model achieves a competitive performance as compared to the current state of the art methods. So we also try to evaluate our prompt as a model in a model agnostic way. Like we try to see whether our prompt is limited for only video llama 3, or it's also helping to boost some semantic to boost performance of other vision language models. For those, we saw that when we added our prompt with the current vision base models, that the performance like GLO score, Meteor, and Rough got improved. And this CEV means the videos has been divided. The dataset contains clip level videos, event level videos, and video level videos, full videos. As you can see, we are getting some better performance whenever the base models are adapted with this chain of anomaly detection thought prompting. So this is the quantitative results on this VANI dataset. As you can see, we are also here achieving a good performance for this detection. See the qualitative results on XT volumes dataset. As you can see that this is an abnormal video. So whenever there is an abnormal activity going in the video, so the model generates a high anomaly score. And when there is a normal activity going in the video, the model generates a low anomaly score. And again, there is a high anomalous activity. So there is a high anomalous score. Similarly, this is another video example where this is a normal video. As you can see that the model is able to generate very low anomalous score along with the explanation that are normal, like it's able to explain what is happening and in a normal way. So let's go some more examples. Another example that we have taken outside the data set. Like this is an open-ended example that we have taken. As you can see that there is a missile attack on some area, and you can see there are the explosion in the sky as well as on the buildings on the ground. So we can see that Homos VAU, that's a fine-tuned as well as the instruction-tuned as well as train-based method, explainer method that's able to generate some explanation, but these are not able to catch what actually is happening in the video. Similarly, this Hawk and this Homos VAD, they are also not able to fully explain the anomalous events that are going into the video. But our model is able to generate the explanation in a more organized way, like it's able to observe what actually is happening in the video, and it's able to detect the anomaly, and at the end it is able to reason why this is an anomaly. Now on the other hand, we have also tried it, we have also showed that in this case with this is a traditional method, like uh, URDMU, that's a traditional vision only method. As you can see that when we pass the example that's outside the XT and UCF-Crime dataset, then it's not able to catch this anomalous event. So it suggests that the traditional methods, non-explainable methods, they lack this contextual information. So these are some concluding remarks regarding our methodology. So we have introduced this Cog-VADU. That's a fully trained free method that models the anomalies via sequential cognitive reasoning. We have provided this combines model agnostic chain of thought prompting with cross-modal ranking. This achieves a strong zero-shot performance, like as we have seen that, and it provides a better generalization on open set examples. And we have also tried to enhance the data quality by re-annotating two major data sets that are available with the thing that are available. Thank you.